are you guys doing? You guys are about a week and a half in now. You guys have a rough idea of what your semester is going to look like. How is it? Pretty good? How does it compare to first year? First year's always asked me what year's the hardest. Is it third year, fourth year, or is it actually still first year?
Online learning.
Online learning? Yeah, I guess last year was a bitch. But it should be better now. We're taking steps in the right direction, hopefully. I say that and then watch it be online next week. Well, hopefully not. I enjoy in person. As I told you guys, I like to see your guys' faces. In Zoom chat, I can't really understand if you guys are getting the material. When I present in person here, I can just look at you and I know. I can tell by the look on your guys' faces if you guys get it or you don't get it. So before we begin, a couple announcements. The only feedback I really got last week concerning the online stuff was they wanted the camera position so that they can see my laser pointer. So we tried to do that. And then what happened in lecture 3 was it didn't record. I thought I pressed record, but obviously it didn't. So I had to go through the slides later on that night trying to sync them up. So that's why you guys will see me be paranoid and just making sure that it's recording over and over again today. But with this focused on the whole board, I should have a nice backup just in case. So that's with the videos. So last week we had our first seminar. How was it? Was it what you guys expected? Or okay, I see one thumbs up. Perfect. So the good news is assignment 1 was kind of weird. It's just that weird linear algebra stuff. It gets better. So if you guys found assignment 1 kind of don't worry, I find it kind of too. I don't even like teaching it. So it gets better. And that kind of starts today, because today we're shifting to a new topic, which is linear maps between vector spaces. So we spent kind of the first week and a half talking about the idea of vector spaces. We said what a vector space was, and we talked about some properties of vector spaces. And we said the reason why we're doing this is because we want to create linear maps between these vector spaces. The best example I can give you guys is if I know the stress in an object, how can I find a matrix to take that stress and give me the strain? Something like that. That's the whole idea here of linear maps. We talked about some properties of them, whether they're injective, surjective, or bijective. And we said moving forward in this course, we want it to be bijective. Because the key with bijective is our linear map is invertible. For instance, if I know the stress, I can figure out the strain. But the key part is if I know the strain, well then I can back calculate and find the stress. That's the key here. That's why we want it to be invertible. If it's not invertible, then we've got some problems on our hands. So today we're going to start talking about the properties of these linear maps between vector spaces. The good part is most of these you guys have seen before. Have you guys heard of determinants of matrices? Yes. See? Have you guys heard of the inverse of a matrix? Yes. So everything here besides maybe one particular portion is going to be more or less review, which is great because after we're done this topic 2 of linear maps, that's when we have our first midterm. You guys excited for the midterm? No? Here's my question to you guys, because I thought about this, and when I do a course, I want the students to feel it's best for them. And I thought, well, as a student, they're probably going to love multiple choice. Is that true? Or would you guys prefer a long answer type test? Who wants multiple choice? Okay, who wants long answer? Why do you guys have to be 50-50? All right, so I can modify it. Long answer might kind of suck because the midterm has to be during class time and it has to accommodate online students. So the midterm will for sure be online. And if it's long answer, then you guys have to deal with trying to scan and upload documents. Now, you guys are probably experts at that because of last year, but is that something you guys would want, or do you guys want to avoid that with all costs? Avoid? So would you guys be interested in a midterm that has a combination of multiple choice, but also numerical answers? Who would prefer that? No one. Got 2 people.
I think you should keep it as close as the example midterms you've got because we like those. We feel safe with those.
All right, that sounds good. So the example midterms are all multiple choice. That's how we used to do it. And then I guess that's how it'll stay. So the first 2 midterms, 25 multiple choice. The first midterm will come up in early October, and it's going to cover basically topics 1 and 2. So we finished topic 1 last week, and we're now starting topic 2. So it's all kind of linear algebra review. Stresses, strains, that's for midterm number 2. We won't have to talk about it. All right, so by this lecture next week, we'll have covered everything for midterm 1. Should be pretty good. And then we're going to get into the fun stuff, which I know you guys have been excited for. So before we begin, is there any general questions, concerns, seminars, assignments, lectures? Are we doing pretty good? Hopefully. How is this class compared to other classes? What's your guys' worst class? 391? 331. Ooh. Yeah, that one's a fun one. All right, so I'm just hoping that you guys are finding this not too bad. I know 8 a.m. suck, but you guys are still here for some reason, so maybe I'm doing something right. All right, so today, if there's no questions or concerns, we're going to jump right in. We're going to talk about the concept of linear maps between our vector spaces. So this slide is actually something I've shown you guys before, because when I tell you guys about linear maps, I want you guys to think of it in a very specific way. We have an input, we throw it into our linear map, and we get an output. That's kind of the basic concept of a linear map. And by definition, a linear map T between two vector spaces V and W. So when you think of two vector spaces, think of V as the initial configuration, the table before I put any load, and the second vector space would be the deformed configuration. After I put the load on this table, it's going to deflect. That would be the second vector space. So we want to try and find a map that goes from the initial configuration to a deformed configuration. And by definition, the linear map must satisfy this property, where if I were to input alpha u plus beta v, where alpha and beta are scalars and u and v are vectors, well, that should be the same as going alpha multiplied by the linear map when I input u, plus beta when I input v into our linear map. Not something you guys really need to know, it's just the formal definition. I'm going to make sure it's still recording. Every time I see a screen flicker, I kind of freak out. Come on. Yep, no, it's not recording. All right. I'll do it later on the computer, but we got this covering everything, so hopefully we'll be fine. Oh, but the screen got bigger. All right. I'm still figuring it out. By lecture 20, we might have it. All right. So the first example I gave you guys when it came to these linear maps is a simple function f of x, where it's equal to a scalar alpha multiplied by x. Sounds nice and simple. And this is one of the things that when it comes to solid mechanics, you guys have already used this linear map. What did you guys learn in Civi 270 when it came to stresses and strains? What was the formula? Sigma is equal to E times epsilon. You guys remember that? Yes? That was a linear map. We have stress on one side, we have epsilon on the other side, and we related them together using E. What is E? You guys remember E? The Young's modulus, exactly. That is a linear map because it relates the two together. Now, if we're looking at Civi 270, and you guys are saying, Clayton, I already know a linear map, why do I need this course? What's the problem with sigma is equal to E times epsilon? What do you guys think? Is there any problems you guys had when it came to Civi 270 when it came to that formula? Let's put it this way. What is E? Give me an example of a numerical value. What is E for steel? 200,000. 200,000 MPa, 200 GPa, whatever you guys take it. The key here, what I'm trying to tell you guys, is when you guys did that, E is one-dimensional. So when you guys were dealing with stresses and strains in Civi 270, it was one-dimensional. If I give you guys a piece of steel, and I were to apply a certain stress longitudinally, you guys can use that formula and you guys can find the strain. But what happens if I take a piece of steel and I pull it, but I'm also applying stresses in other directions? That's what we're going to get into in this course. In Civi 270, we introduced it, but for a uniaxial case, only one dimension. Well, unfortunately, we're in 3 dimensions, so we have to figure out a way to find those stresses and strains in 3 dimensions. That formula, sigma equals E times epsilon, is going to be the exact same in this course. The only difference now is sigma and epsilon are going to be vectors, And E is going to be a tensor or a matrix, as you guys are going to see. So when we look at this formula, I can give you guys an example, and I can say that f of x is equal to 7x. If you guys were dealing with stresses and strains with E, this could be 200,000, something like that. So what I can do is I'm going to take an input, put it into my linear map, and then I get an output. This is, again, the whole concept of linear maps. I can move it into 2 dimensions, so R2 to R2, and say that, all right, my linear map is now a matrix. This is the key here. So I can have kind of a sample calculation, and it follows the exact same procedure. I take an input, I throw it into my linear map, and I receive an output. So I'm hoping that this is making sense to you guys. Now, again, I want to clarify this. As the course goes on and on, I'm going to say it more and more. Whenever I talk about a linear map, I will probably refer to it as a tensor. That's the formal or correct definition of it. What happens is second-order tensors, which are all these things we're going to be talking about, they're the same as matrices, and they hold the same properties. There's only very specific cases when we're going into higher-order tensors. Very specific cases. So if you guys see me say tensor, well, I'm referring to a matrix. If you guys see me say matrix, well, I'm referring to the tensor. They're interchangeable unless we get into those specific cases. When we do get into those cases, I'll be sure to tell you guys, hey guys, this is a special case. This is not a matrix, it's a fourth order tensor, something like that. So now let's talk about basically the form of linear maps. So if M is a linear map from Rn to Rm, M has M by N matrix representation. You guys are saying, of course I know this, Clayton. I've seen matrices before. It's going to look something like this. Now what's nice for us is even though I have it to basically infinite dimensional vector space, we're going to mainly be dealing with 3x3 square matrices. Why will most of our matrices or tensors be 3x3? 3 dimensions, exactly. We're not dealing with 4th dimension or 5 dimensions, anything like that. So for a 3-dimensional case, this will be usually 3x3. And if it's a 2-dimensional case, this will be 2x2. Now, that's typically. There will be some exceptions. For instance, when I'm converting from stress to strain, stress and strain will be 3x3 matrices. But the matrix relating them, that E matrix, that'll turn out to be 6x6. Or it could be even higher, something like that, depending on the situation. So mostly we'll see 3x3. Now, here's the key. Because when it comes to exams and what you guys will see, these little properties are going to be the key to your exams. You guys will be able to figure out these properties on your own. They're very simple. But if you know them, you can figure out exam questions very fast. These are usually the tricks to exam questions. I will tell you that this map is bijective or invertible, and from there you guys conclude many things right away without actually having to do any calculations. So if our linear map is bijective or invertible, which again, that's what we want in this particular course, it has some properties. The first is that it is injective. What does injective mean? What do you guys think? What does injective mean? Who remembers last lecture? I guess 2 lectures ago. Exactly. There is an output for every input and vice versa. That's going to be very important to us. If I put a force of 200 kilonewtons on this table, it's going to have a deflection. Let's say it's 3 millimeters. But if I were to tell you guys that the deflection of this table was 3 millimeters, well then I can back calculate and figure out that the force I applied was 200 kilonewtons, something like that. The second one is that it is invertible. And this is kind of the most obvious one, because if I tell you the map is invertible, it's invertible. Now this is the one that's going to be kind of the only new thing in today's lecture, is that the kernel of M, this linear map, is solely the 0 vector. So the kernel is the only thing that I'm thinking you guys may not have seen before. Have you guys heard of the kernel of a matrix before? No. So basically the kernel of a matrix is the set of vectors that map to the 0 vector. Basically what this means for an invertible map is that the only inputs that should give me 0 are 0. If I were to look at this table and I wanted 0 deflection, the only input that I can have to this table is 0 force. That should be it, and vice versa. If I were to even put 0.0001 kilonewtons of force on this table, there should be 0.0001 or whatever millimeters of deflection. The only time I should have no deflection is when I have no force, and vice versa. That's kind of the kernel of the matrix. And then this is one that will get you guys in an exam, I guarantee it. The n vectors forming the square matrix M are linearly independent. So this is going to be the key for these invertible matrices. If I were to give you guys a matrix M in 2 dimensions or in 3 dimensions, we can create 2 vectors, or 3 vectors if it's 3 dimensions, from this matrix M. I can say, all right, row 1, A1 and A2, I can make that a vector. Row 2, B1 and B2, I can make that a vector as well. And the key here is that these vectors are going to be linearly independent. Now that doesn't sound like a lot, but what does this mean? If something is linearly independent, what else do we know about it? What should the dot product between them be? I'm not going to tell you guys because I want you guys to study. But you guys know what I'm saying when it comes to exams? When I give you guys one piece of information, you can start concluding other pieces of information that will help you solve it. If you guys don't know what linearly independent means, well, then you guys won't be able to conclude this property. And if you guys don't even know that the matrix is linearly independent, well, then you guys might be really stuck. So it's kind of these properties that really get you guys in exams. And we're going to talk about a lot more of them. So that's the concept of bijective linear maps. But now we're going to start talking about some actual properties of them. And this is great because this is something we talked about in Math 102. Again, you guys said you all heard of determinants. But what is a determinant? What do you guys use it for? Who knows, right? Math 102 says here's how you calculate it, but I don't know. I'm a math guy. I just know it's a determinant. Now we're going to actually talk about what it physically means in our reality. So let's go into determinants. The determinants of a matrix is a real valued function that indicates 2 things. First, the invertibility of a matrix. That's going to be important to us, right? We want our matrices to be invertible. And then the second one, which is more of a physical meaning, which I like to see, is the change in area after a linear transformation. If I were to take an object and I were to squish it, the determinant will actually give me some sort of indication of how much I squished that object. So that's going to be useful when we talk about strain. Now, when calculating determinants, it's very simple. Were any of you guys in my Eng 130 class? None of you? I don't think any of you guys were. Well, the way I do it is I make a fish, right? Fish method. And I kind of talked about it last lecture because I said, well, if I want to show you guys a cross-product proof, I'll show you my method, but it's controversial because the way I describe the fish is the Jesus fish. You guys know this fish like that? Something like that. It's something that sounds funny, and you guys are saying, oh, he's getting a little edgy, but you'll never forget it. As soon as I made it edgy, you guys are like, oh, okay. So all you guys need to do for determinants is make a fish. Start at A1, swoop down to B2, come up to A2, and back to B1. So again, just making a little fish. If I were to write it down, I can say the determinant of a matrix is equal to this. So this is just a matrix now with absolute value signs that signifies the determinant. And it's equal to A1 times B2 minus A2 times B1. Again, I just made a fish. A1 to B2 minus A2 times B1. That's nice and simple. What about 3 by 3? Is it still going to be fish related? What do you guys think? Yes, it's going to be fish related. So if we look at this matrix C, we have B2 times C3 minus B3 times C2. Well, B2 times C3 minus B3 times C2. And then all I did was I multiplied it by this coefficient up here. So what I do when I do the cross product is if I'm interested in the first component, I cross out this entire column, and then I make a fish on what's left. So I cross this out, B2 times C1 minus B3 times C2, and then I multiply by A1. Then I can move to the second component and kind of do the same thing. B1 times C3 minus B3 times C1, and then multiply by A2. Now, does this formula look familiar to you guys? Yes. What is it? Who remembers last lecture? This is one of the formulas I showed you guys last lecture, and you guys said, I've never seen that before. But then I show you guys now, you're going, oh, wait a second. This is that triple scalar product, where we take A and we dot it with B cross C. All right? So if you guys want to find the determinant, this is how you guys would do it by hand. But this is when we get into the fun. So today, this week's assignment. I said last week that everything will now be basically Mathematica. When I look at my own solution guides for every assignment, I don't have a single Word file, I don't have a single Excel file or a single piece of paper. I just have a Mathematica file for every assignment. And this is one of the reasons why, as you guys may guess on your assignment, actually let's put it this way. Who got one of their assignment questions in number 1 wrong? Yeah, everybody. That's the purpose of the assignment, to try it again. Now when you guys started a new preview, did you guys have the same questions or did it change on you guys? It changed. So of course I got an email or two, hey Clayton, can you change it so that I don't have to keep repeating it? Well, the answer is going to be no. It's a trade-off. I give you guys unlimited attempts in the assignments, and then you guys have to really make sure you guys understand the material. That was kind of the trade-off. If I was solely interested in marks, well, I'd give you guys 1 attempt, and you guys would find out the hard way if you guys were wrong. But then I get complaining, well, Clayton, it takes me forever, I have to deal with Yong, I can't do this. Well, what's nice is because assignment 2 and all the way to the end is all Mathematica. I did the assignment, I go through to make sure that it's coded correctly, and I'll probably still find errors after you guys try it. But what basically happens is I was able to solve it 3 times in 15 minutes, the whole assignment. Because once you create the Mathematica code, and you guys get it wrong, and you guys retry it, all you have to do is change your inputs. The code should take care of the rest. If you guys get it wrong, it's not your inputs, it's usually your code. So basically, you input your values, run your code. If it's wrong, change your code, change the input, try again. And as you guys will see, it's very cyclic. The Mathematica portion of this course is going to become quite heavy. But then I was looking at Yong's teaching history, and I saw that he taught 295, which is kind of a shame because I thought you guys took it with Dr. Sammer. Who took it with Sammer? Perfect. Who took it with Yong? You poor guys. The reason why is because I know Sammer loves Mathematica. So who knows Mathematica? Exactly, from Sammer. Does Yong use Mathematica? No. MATLAB. I'm not even surprised. So it's one of those things that I will teach you all the Mathematica you guys need to know, but if you guys have already experienced it with Dr. Sammer, you guys will have assignment 2 done in 10 minutes. It's very simple. This is the stuff on assignment 2. So I'm not collecting any sort of work in these assignments. So if I were to ask you guys for a matrix, if I give you guys a matrix and I ask for a determinant, who's doing this by hand? No one. Everyone's going to go to Mathematica because all you need to do is type in your matrix and then type in DETM, and it'll give you the determinant. That's all you guys need to do. So even though I'm showing you guys the theory, I don't expect you guys to write the theory down in the assignments. It's going to be all Mathematica. In the seminars this week, I will show you guys the commands in Mathematica for these particular things, because if you guys took it with Yong, you guys have no idea. All right, so hopefully that clears some things up with the assignments. So we have 2 different matrices. We're not going to get into 4x4 because, again, we're not really dealing with that vector space. Now, matrix invertibility. Again, the first key I have for determinants is this. It indicates invertibility. Do you guys remember how we do that based on determinants? Equal to 0. All right, so that's correct. So what happens if our determinant is equal to 0? What does that signify to us? In terms of invertibility. It's not invertible. Exactly. So if our determinant is equal to 0, our matrix is not invertible. Makes sense, right? If our determinant is not equal to 0, our matrix is invertible. Now this is something I want to talk about really quick because students really don't like negative numbers. For some reason they think if it's ever negative, it's not invertible. If I were to get my determinant as negative 50, is my matrix invertible? Yes. Will we have a problem if our determinant is equal to negative 50? Who thinks we'll have a problem? Who thinks it'll be good to go? It actually will be a problem, as we'll see later on. One of the second properties we talked about is our change in area. So this is something that mathematically there's no problem. But when it starts coming to the physical world, there will be a problem. A negative change in area basically means something folds in upon itself. That's not physically possible. If something were to get squished, a coefficient describing something getting smaller is 0.5. It gets in half. If it were to get longer, a coefficient would be something like 2. But we can't have negative because it means it inverts upon itself. So this is something we'll talk about when it comes to strain, but I want to let you guys know early to show that these determinants actually have purpose. They don't seem like they do, but they actually do. So now determinants have properties. I guarantee that something on this slide will be in one of the multiple choice questions because it's just too easy. It's too easy to get you guys at these. So if M is a 2 by 2 matrix, the following is true for any n, m, and any scalar alpha. So n and m are 2 by 2 matrices, and alpha is any number. The first is the determinant of n times m is equal to the determinant of n multiplied by the determinants of m. It's again these properties that get you guys in exams. The determinant of alpha times m is equal to alpha squared multiplied by the determinant of m, and the determinant of I is equal to 1. So I didn't really give you guys what I is, but you guys remember I? The identity matrix, 1, 1, 1, the rest are zeros. Perfect. Now what about transpose? You guys remember transpose? What happens when we transpose a matrix? Exactly. We swap the rows and the columns. So component ij, after we transpose it, is going to now be ji. Now the horizontal 1, 1, 2, 2, 3, 3, are those going to change? If I were to take entry 1, 1 and transpose it, is it going to change? No. You can swap 1 and 1, but you still get 1, 1. So it's only going to be those off-diagonal ones that swap with each other. Now let's say that I have M12, and this would be M21, and they were the exact same. With transposing a matrix that is what we call symmetric, where the off-diagonal components are equal to each other, will transposing that do anything? No. So do you think I'm showing you guys something useful right now? No. As we're going to see, the matrices that we deal with in this class, it gets a little bit different in grad school. But for linear elasticity, where nothing cracks, nothing breaks, our matrices are going to be symmetric, meaning that 2, 1 is equal to 1, 2, 3, 1 is equal to 1, 3, etc. So transposing effectively does nothing. But we are going to use the transpose in one specific case. So I'm still going to show you guys it. And again, the whole idea of a transpose, we're just flipping the subscripts. Should be nice and easy. Now how about an exam? Clayton, this is too easy. How can you guys test me on something so easy? Well, we got properties. That's what I'll always get you guys. So for any two matrices, n times m transpose is equal to m transpose times n transpose. N plus m transpose is equal to n transpose plus m transpose. And n m transpose ij is equal to the summation from k equals 1 to n of n I k m n j k. So I showed you guys this, you guys were sleeping. I showed you guys this, you were sleeping, and now you guys are scared. This third one is more of a proof that we use a lot in graduate school, solid mechanics. I promise you guys I won't be a dick and throw this one on an exam. That's a bit too mean. So just focus on these two right here, okay? All right, good exam question. So let's talk about the kernel of a matrix. This was what I predict was the only thing that's going to be new to you guys. So the kernel of a linear map M between two vector spaces V and W is the set of all vectors that are mapped to the zero vector. Again, this is something we don't want. If something has a kernel, it means it's not invertible. What does a kernel mean? Well, it says if I were to put 300 kilonewtons of force on this table, I get zero displacement. Well, we know that's not going to be true. It's not a rigid body. So we don't want things to have a kernel. But you guys have an assignment this week, so you guys have to learn how to find a kernel. So we denote it as this. KER of M is equal to the set of vectors X, where when we map them in our linear map, they return 0. Now, this is the key thing. Only matrices that are not invertible, the determinant of M is equal to 0, have a kernel. The reason why is because if it is invertible, there should be only one thing that maps to 0, and that is 0. So if the only thing that maps to 0 is 0, if my input is 0 and my output is 0, that is invertible. But if there's anything else that maps to 0, it has a kernel, and it's not invertible. So let's do an example. This will look very similar to your guys' assignment 2. You have a matrix just like this. M is equal to 1, 1, 6, 6. So if I were to ask you guys about this matrix C, the first thing I would ask on an exam is it invertible? How do we determine if it's invertible? Determinant, exactly. So I look at this matrix C, I say, okay, not too bad. I take my determinants, I'm just doing a fish, 1 times 6 minus 1 times 6. Uh-oh, it's 0. So this is your first idea that it has a kernel. Not invertible, has a kernel. I say, all right, Clayton, but how do we solve for this kernel? Well, we're basically going to solve this equation over here, where we're taking our linear map M, multiplying it by a vector, and again, it must map to the 0 vector. So if I were to write this out, we have 1, 1, 6, 6, that's given to us, multiplied by some vector is equal to 0. I have two equations, two unknowns. Is there going to be a problem? Nope, you guys are brave. There's going to be a problem. Infinite solutions. So what you guys are going to see is the kernel is a line. Now in linear algebra, if I want to describe a line, how many vectors can I use to describe that line? Infinite. If I were to have a line that's infinitely expanding, I can just take a little vector right here, or I can take a little vector right here. I can do basically anything I want. So this is going to be the first trick to kernels. It's always going to have infinite solutions. So what you guys need to do is you guys need to set one of the parameters equal to something. In this case, I left it parametric and set it to alpha. But in your guys' assignment, you guys can set it to, I don't know, 1, something like that, whatever you guys want. Because now that you guys know V2, you guys can go back to your system of equations and solve for V1. If I were to input alpha into this equation, I would solve for V1 as negative alpha. So what this would mean is that the kernel of M is equal to a vector negative alpha, alpha, where alpha can be anything. This would be the kernel of my matrix. Make sense to you guys, hopefully? Now, this comes to the question of Clayton, what about the assignment? It's no secret, the assignment will ask you guys to solve for kernels. Now, will you guys have a parametric? No. Which is a problem, because everyone will say, well, there's infinite solutions. How can I solve it? It's just like assignment 1, that part C of 3 or whatever. You guys just have to give me one of the possible solutions. So you guys can set alpha is equal to 1 and then solve for V1. You guys can set alpha is equal to 100 and solve, it doesn't matter. Now what typically happens is you guys are going to use Mathematica. There's a very nice Mathematica command that will return us with the kernel of a matrix. And what it does is it always sets the last component of a vector to 1. So you guys will have some number, and then 1. Or if it's 2 dimensions, you'll have some number, and then 1. That's it. All right, I want to clear that up with the assignments. I'm going to get a lot of questions. Hopefully that's not too bad for you guys. Now, one thing I want to mention about the assignment kernels really quick, and this will also go to eigenvectors. There is one little coding problem on the assignment that's just kind of difficult to solve for. Sometimes these kernels will pop out just a regular number, let's say 7, an integer. The code in the assignment is only focused on double point numbers. So if you guys were to get 7, when you guys input it, please input it as 7.0. Otherwise, it'll say that you're wrong even though you're right. All right, so I just want to save you guys a lot of time on the assignment. I'll mention it again in the seminars. Whenever you guys input vectors into the assignments, put a 0.0 or something. Best way to remember is when you when you output this in Mathematica, it'll even say 1.0. It won't ever just give you 1 or 7, it'll say 7.0. Always input it as actual double precision numbers. So let's talk about eigenvalues and eigenvectors. You guys have seen this before, right? No, I know you guys are lying to me. I know you guys have seen this before. I did undergrad here. Eigenvalues and eigenvectors. What are they? Do you guys remember what they are? No? You guys just don't care? It means nothing? Well, this is going to be very important. Remember in Moore's circle, we said we can rotate it so that we get principal stresses. Well, it turns out when I gave you guys a stress matrix, the eigenvalues and eigenvectors of that stress matrix are actually those principal stresses. And we're going to talk more about that a little bit later. So an eigenvector of a matrix M is a vector that when transformed by M retains the same direction. That's going to be the key here, retains the same direction. The magnitude of expansion or contraction of that vector after transformation is the eigenvalue. Clayton, words, I don't like words. Half you guys are sleeping, I don't blame you. So let's look at an actual picture. Let's say that I had these two vectors, u and v, and I were to transform them by m. So these are the original vectors, the faded ones. So if I were to look at u here, and I were to say that after I apply m, it changes into something like this. Would u be an eigenvector? No, because it changed direction. That's the key here. Let's look at v. If I were to take v and multiply by m, or I guess vice versa, and I were to get this, would this be an eigenvector? Yes. So this is the key here. It doesn't change directions. So what I can say is this mv, well, this is actually equal to some scalar component multiplied by v. Because again, v has the same direction. So instead of multiplying it by a matrix, I just have to multiply it by some sort of coefficient to expand or contract it. That's all I have to do. So as the direction of v did not change after the matrix transformation, we would say that v is an eigenvector of m associated with an eigenvalue of lambda. Make sense? How do we calculate them? Well, all we need to do is solve this equation. So you guys now know determinants. You guys know that we have a matrix m, and all we're going to do is subtract lambda times I. Now, this looks pretty gross, but it's basically going right back into our determinant formula, and then every diagonal component, we're just going to subtract lambda. So an example, if we had this 2 by 2 matrix, and we were to throw it into this formula here, it's going to look something like this. So again, only this diagonal row, we're just going to subtract lambda. If we were to take the determinant of something, I can expand it into this. And what happens is you guys get a quadratic equation, and you can solve for lambda using quadratic formula. Pretty simple. But let's be honest, you guys will never do this because who knows how to get eigenvalues using Mathematica? What's the command? Do you guys know? Who wants to take a shot in the dark and guess it? Eigenvalues. That's all you guys have to do. Define your matrix M and then just go eigenvalues M. And it'll give you the eigenvalues. So this is why assignment 2 is a piece of cake. How about a 3 by 3? I have M now, 3 by 3. Well, same thing as before. I can go to the determinants of m minus lambda I. And again, I'm only subtracting lambda from these components right there. I get this ugly, ugly equation. But it's cubic. We can actually solve for lambda. So if it's a cubic equation, how many values of lambda should I get? 3. Exactly. Will you guys ever solve this? Well, probably not. You guys are going to, again, throw it into Mathematica. It's nice and simple. Eigenvectors, on the other hand, they're a little bit more challenging for students to find. So an eigenvector p associated with eigenvalue lambda of a matrix can be solved for using the following equation. M times p is equal to lambda p. So at this point, the first thing you guys would always do is solve for the eigenvalues. So you would have m from the question, you would have lambda, so you just solve for it. The only unknown is p. So when we go to a 2 by 2 scenario, we were to write this equation. It's 2 equations with 2 unknowns, p1 and p2. 2 equations, 2 unknowns, you guys can solve for it. Well, there's a problem. There's going to be infinite solutions. The reason why is because, again, the direction is just defined by a line. And that line can be defined by many vectors. It's the same problem that we had with kernels. So when solving for these, all we have to do is we have to assume a value for p1 or p2 and then solve. This will be very apparent in your assignment when you use Mathematica because the last component of every eigenvalue will be 1. That's what Mathematica does. It sets the last value equal to 1, so in this case it would set p2 equal to 1, and then it would solve for p1. The same problem would happen for a 3 by 3 matrix, this over here. If I were to write it out as follows and solve, I can create my 3 equations, 3 unknowns. Well, what we would have to do is assume a value for P1, P2, or P3. Again, if I were to throw this into Mathematica and I were to look for this vector, it would be some number, and then 1. So it makes it hard for instructors because if there's infinite solutions, we would have to check all your guys' solutions because they could all possibly be valid. Now, if you guys were an instructor and you guys were to try and make everyone have the same answer, what would you guys ask for when it came to these eigenvectors? There's something very common. I don't ask for it because I make everything via Mathematica. What do you think what can we do to make every eigenvector the same for all you guys? Normalize it. So typically, if you guys were to look at any sort of literature, any solid mechanics book, linear algebra, after they find this eigenvector, which is some number 1, they normalize it into a unit vector just to define that direction. I wanted to throw it out there, but again, in your assignment, you don't have to normalize it. You guys can just throw it in however Mathematica gives it to you. Or if you want to solve it by hand, you can throw it in too, but you guys aren't going to solve it by hand. You're not fooling me. All right, so the last thing we're going to talk about is a matrix change of basis. You guys thought that was done? Well, no, it comes back. And this is actually the more important change of basis. The change in basis of a vector wasn't too bad. As we saw, if we wanted u prime, we just take q and multiply it by u, everybody was happy. What happens when I want to change the matrix, or change the basis of a matrix? First of all, you guys probably don't even know what I'm talking about. So let's go into a picture. Let's say that we have an original basis set, E1 and E2, and in this basis we have U. All right? If I wanted to, I can take U and transform it via my linear map M to get a second vector V. This is kind of what we talked about today. This is nothing too crazy. What happens if we take this scenario right here and we do our change of basis? So again, all I'm doing is I'm now rotating the basis set to form E1 prime and E2 prime, but I left my two vectors the exact same. That's the key here. The vectors didn't move. If I were to trace them from here to here, over to here, they didn't move. In this new set, I have U prime and V prime, but here's the trick, and this is what a matrix change of basis is. If I wanted to relate U to V, is it going to be using the same M as I did over here? No. These directions are set. But since the coordinate system is now changed, I need a new matrix to relate the two together. So this is what I'm talking about when I talk about a matrix change of basis. The vectors change, U prime, or U to U prime, V to V prime, but also the matrix relating the two vectors, M, also changes to M prime. So that's the question here, is how do we solve for that M prime now? If I were to ask for U prime, you guys are laughing. Not laughing anymore. So if I wanted a linear map in a new coordinate system, we can actually derive a simple formula. Let's start off with this nice expression right here. V prime is equal to M prime times U prime. That comes right from here. I didn't see you guys have a problem with that. Does anyone have a problem with this? Rubbing anyone the wrong way? No? Not yet? That's typically derivations, not yet. So we're going to take this formula and we're going to look at U prime. So that's this over here. Now, when I went from U to U prime, is there a nice relationship between them? What do you guys think? We did this last week. If I wanted to go from U to U prime, what is my formula? I kind of hear you guys whispering. U prime is equal to Q times U. You guys remember that in your assignment? So what I can do is I can take this U prime and I can go to old reliable over here, Q times U. Hopefully there's no problem thus far. Now I'm going to look at V prime. What can I say about V prime? It's equal to Q times V. Again, if I can go from U to U prime, I can also go from V to V prime. So that's all I did here, was I went U prime is equal to Q times U, and V prime is equal to Q times V. Have I lost anyone yet? No? Perfect. So now we're going to say, all right, this doesn't look too bad. What about V? Do we have a nice expression in the regular basis set for V? Yes, we know that V is the linear transformation of u by m. So I can take that and I can substitute this. Now when we look at this, and when we look at variables, I had u at the end and I had u at the end. Can I cancel them out? Ooh. Now it's getting real. Can I cancel those two u's out? They're vectors though. They're not scalars. The answer is yes, you can. It's only matrices that you guys worry about just canceling them out. So u cancels on both sides, and I'm left with q times m is equal to m prime times q. So I know q, that's something we always know. Remember, counterclockwise or clockwise, we can figure out q. M is my original matrix, which will be supplied to you guys. The only unknown now is m prime. So how can I solve for m prime? What do I have to do to the q beside it? How can I move that q to the other side? Inverse. Did I inverse it? No. So this is where this course starts to take a turn into what the hell. I have qm, which is over here, and then instead of inversing it, I want q transpose. This is why I showed you guys transpose, because this is the only real applicable situation you guys are going to use. Now, why did I go transpose instead of inverse? Well, it's something we're going to cover next lecture. And this is something that I guarantee you will be probably 2 or 3 questions on your exam. Q is orthogonal. Now, orthogonal matrices have a very special property where the inverse of them is equal to the transpose. When we talked about transpose, you guys all said it was a piece of cake, right? You guys are saying, oh, just flippity floppity, all everyone's happy. Who wants to inverse a matrix? Who wants to inverse a matrix? No one. Mathematically. You want to inverse? This guy knows mathematics. Inversing matrices is like, it's ass, let's be honest. No one wants to inverse matrices. So this is a nice, simple formula for us. The idea of orthogonality is something we're going to cover next lecture, and that'll be on your exams. Because orthogonality allows us to conclude many, many things about a matrix. One of them being that the inverse is equal to the transpose. I wouldn't give you guys the inverse yet, because we haven't talked about it. So next lecture, we're going to start by talking about the inverse, and then we're going to start talking about the idea of these orthogonal matrices or orthogonal tensors. They have a lot of very nice properties. Any matrix that you guys have seen in this course associated with rotation or reflection are going to be orthogonal, and then they're going to possess this nice property right here. So is there any questions about the content today? Because now we're going to move into some examples. Might even get out of here a little bit early. No questions? All right, you guys must be geniuses because I was lost at the first slide. All right. So I'll keep it over here. So I'm going to try and record this for extra clarity. But it probably won't. That's okay. I have this focused on the screen now, so it's my safety option. I'll move the mic over here. And we're going to start talking about some fun questions. So we only have 4 questions to do today. Again, we might get out a little bit early. I know that's what you guys want. So let's talk about this quiz right here. It says, consider the new basis set B prime, which is equal to E1 prime and E2 prime, where the new basis vectors, where the new basis vectors are 30 degrees, or rotated 30 degrees counterclockwise from the original basis vectors E1 and E2. Determine the following components in the new basis system. So all this basically is change of basis. But we give you 2 different scenarios. The first one is U, which is a vector, and this is what we covered last week. How to find the new vector components in a new basis system. The second one, part B, isn't a vector anymore, it's a matrix. So how can we find M prime in the new basis system? So is there any questions concerning this question? Because I'm going to have to scroll down. If you guys are reading this question, what would be the key piece of information from the red writing that you guys would want to highlight? Counterclockwise. That's going to be important to us. So we'd say, all right, we're doing counterclockwise. That is the ugliest yellow I've ever seen. All right. And probably, of course, 30 degrees. All right, not too bad. So let's go down to these two and let's talk about it. So if I want to find u prime, and I was given u, which is a vector, what is my formula? How can I find u prime? If I were to say u prime is equal to, what's the formula for change of basis of a vector? QU, exactly. Good thing it wasn't F. Q times U. So if I know Q, can I solve for U prime? Piece of cake. What about M? So let's switch colors really quick. I'm not sure if I used pink or purple. Oh, that looks the same. All right. What about M? If I wanted M prime. QM, Q transpose. Exactly. We just covered this in class today. Q, M times Q transpose. So if I were to look at this question as a whole, I have U, which I know. I have M, which I know. The only other thing I don't know is going to be Q. Now, do you guys need to derive Q, or do you guys already have it written down somewhere? Have it written down somewhere, exactly. So let's go to a different color. Let's go blue. How does this turn up on the screen? All right, that's not too bad. So Q is going to be equal to, and we know for 2 dimensions it's going to be a 2 by 2 vector. So what would be the first entry in the top corner, top left? Cosine of theta. What about the bottom right? So this entry right here. Ooh. That entry right there. Cosine, exactly. So this is nice because counterclockwise or clockwise, it's always going to be positive cosine. All right? So over here we have cosine of theta. Now what are the other 2 entries going to be? Ignoring the negative sign. Sine, exactly. So we're going to go, all right, this is going to be sine of theta. And this is going to be sine of theta. So I'm just going to close my brackets really quick. Oops. Come on, work with me. So the key piece of information that we're going to have to use is that we have a counterclockwise rotation. So which sign is going to be negative? Top or bottom? You guys know this. It's a piece of cake. Now here's a question, because I kind of touched upon it, and you guys are going to see this in the assignment. In this question, we are rotating our basis set counterclockwise. What happens if I was rotating the vectors counterclockwise? Would this Q still apply? Remember, right now I'm rotating the basis vectors. I'm not rotating U. But if I wanted to rotate U, could I use this Q? Who thinks yes? Who thinks no? Exactly, no. But if I wanted to rotate the vector U, not the basis vectors, but just U, could you guys give me the Q for that? You guys can. It's actually just the opposite. So if I'm rotating my basis vectors counterclockwise, it's going to have the same Q as if I'm rotating my vector or my shape clockwise. We're going to talk about this in the seminars this week, so it's kind of one of those little fun facts. This is why I got so many emails, everyone saying, Clayton, you wrote it wrong. The negative should be up top. The only problem is when they would send me the sketchy website that they got their math from, they were talking about rotating U and not the basis vectors. So if I wanted to rotate U, all I would do is I would take this negative sign and throw it up there. Or if I wanted to rotate U clockwise, I would just use this formula right here. Make sense to you guys? It's not something you guys will really need to know besides assignment 2. Just a little fun fact. I'll show you guys in the seminar pictorially how it goes, and you guys say, oh, all right, Clayton, that's easy. So let's look at Q. What's my only unknown in Q? Theta. Are we given what theta is? Yeah. Exactly. So theta in this case, we were given as 30 degrees. So do I know everything I need to know for Q? When you guys look at the screen, I'm scared to stop recording or something. All right, so Q is equal to, and let's see how much you guys know trig. What is cosine of 30? Approximately in decimal form. 0.866. I didn't expect you guys to know that, don't worry. What about sine of 30? 0.5. That one would be good to know. So 0.5, negative sine of 30, so negative 0.5. What's cosine of 30? 0.866. So we have Q, and if I wanted to solve the questions now, all I need to do is throw it into Mathematica or even throw it into a calculator. So we got U prime is equal to Q times U. Well, we know Q, we know U prime, just throw it into your calculators. So you say, all right, U prime is equal to Q multiplied by U, which is equal to, and once you guys throw everything in, I get 1.366, and then I get 0.366. So another thing I want to talk about really quick, because this would be a good time for you guys, is I've kind of hinted in the assignments you'll use Mathematica. Now, some of you guys with Dr. Yong said that you guys used MATLAB. It's the same thing. When you multiply a matrix, do you have to use a special command? Yes? No? Yes. In Mathematica, it's the same. So for those of you who don't know Mathematica and are going Q star U, you're not going to get anything productive. How do I multiply a matrix in Mathematica? Two matrices together. Who remembers? Dots, exactly. So if I were to type Q and define it in Mathematica, and I were to go U and define it, all I have to do for U prime is go Q dot, or a period, U. I want to make that clear, because someone's going to put star and say, I don't know why I keep getting it wrong. It's because you have to define it correctly. So for M prime, we know that this is going to be equal to Q times M times Q transpose. And when you guys throw everything into there, you guys should get 1.866, 1.5, negative 0.5, and 0.134. So if I were to give you guys this on an assignment, or not an assignment because you guys have limited attempts, and an exam, would you guys be able to do this? Yeah? Shouldn't be too bad. You think you'll get something this easy on exams? Yes? Yeah? It leads to kind of a funny topic, because one of the things I keep getting asked about is bonus marks on assignments. So every assignment, there's 10 assignments, and each one is worth 10 marks. Now, if you guys look at your assignment this week, it's out of 12, because there's 2 bonus marks. What happens at the end of the day is every assignment is worth 10. So if you guys get everything correct, including the bonus question, you will have 12 out of 10. You will get over 100%, which is nice, because let's say that I got 12 out of 10 on assignment 1, but 8 out of 10 on assignment 9. Well, those 2 marks that you banked on assignment 1 can make up for it in later assignments too. But at the end of the day, when I total it up out of 100, do you think I'll let you have over 100 out of 100? Who thinks no? Who thinks yes? Yes, why wouldn't I? So that's what I try to tell everyone. Bonus marks are great because you guys can get over 100% and get the additional percentages. And then I'm met with, well, you're going to curve the class, so if everyone gets the bonus marks, does it even matter? Who thinks I'm going to curve the class? Ooh. As an instructor, I don't have to curve the class. If you guys put in a good effort and you guys are all doing great, who am I to go to the person who got 90% average and say, sorry, but that's a C? No one wants that. So let me just put it in perspective. You know, on Bear Tracks, when you go see your letter grades, it shows the average of the class in GPA. What's it typically out of 4? The averages. You guys ever looked at those?
3.1.
3.1? You guys want to know what my average was for my class I taught in winter? 3.84. So if you guys put in the work, I'm not afraid to give you the marks. I want you guys to know that. It's all about putting in the effort. So let's move on to the second question before you guys get too excited. So the second question, which of the following matrices are invertible? How would I determine if a matrix is invertible? Determinant. So all I have to do is go, the determinant of M is equal to something. So if I were to go the determinant of M, again, all I'm doing is making a fish. So I'm going to go 1 times 1 minus 0 times 0. You guys see where the fish starts to come into play? It's very important. We go 1 times 1 minus 0 times 0 is 0. I get my determinant is equal to 1. Is this invertible? Who thinks yes? Yes. So this is invertible. What about the second one? Again, all I'm going to do is make a fish. 1 times 0 minus 0 times 10. So I'm going to go 1 times 0 minus 0 times 10. I get that's equal to 0. Is this one invertible? No, because I have my determinant is equal to 0. So therefore, not invertible. For the next question, if I were to draw my fish, and then I were to find the determinant, I would get that this one is equal to negative 40. Is that invertible? Is that physically possible? No. So it is invertible because it's not equal to 0. But as we'll see, getting a determinant that's negative is physically impossible. Again, it means the object inverts upon itself. It means that this wall would somehow come through this wall. Doesn't make any sense, right? So therefore, this one would still be invertible. But again, I just want to let you guys know that a negative determinant isn't a good thing. And for this last one, we get the determinant of M is equal to 0. So therefore, what's it going to be? Who thinks not? Who thinks it is? Not invertible. Perfect. So this should be nice, easy questions come exams. Now, this type of question, I love on exams. And this is why I kept hinting at you guys when I discussed properties. So expect to see questions in this kind of format. Let M be an element of M2. What does that basically tell you guys? What is the dimensions of M as a matrix? 2 by 2. Be a matrix whose kernel, I guess I can, did I zoom in? That's why. Whose kernel contains only the 0 vector. What does that tell you guys? There's only one type of linear map where the kernel is only the 0 vector, and that is an invertible map. So this is where everything starts to become chained. I don't tell you that this is invertible, but by telling you guys that the kernel is only the 0 vector, you guys should go, oh, ding, 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 invertible. So now that we know that it is invertible, we can go through the statements. Is this true? The determinant of M does not equal 0. Is that true? Yes. We said if we just did it up here, if the determinant is not equal to 0, it's invertible. So this right here Absolutely true. Part B is even the simple part where it says it's invertible. Well, we said that's kind of the key piece of information right here. So if you guys see A and B as check marks, we already know what the answer should be, right? It's going to be all of the above. Do I recommend just jumping? No, as long as if you make a mistake. The worst is when you get something like this. That happens in exams and everyone freaks out. All right. And the last one, M is bijective. Well, yes, we said the bijective invertible, they're interchangeable. All right? So these kind of questions expect to see on the midterms and expect to see in the finals. Sound good? Now let's get into a fun one. Find a matrix, and again, what is the size of the matrix if it's an element of M2? 2 by 2. Find a matrix that does not have real eigenvalues. Ooh, now it's scary. And then it follows up and says, can a symmetric matrix have non-real eigenvalues? So we're going to talk about that one right now. So the first key piece of information, and let's switch to green, is this part right here. This tells you that our matrix is 2 by 2. If you do 3 by 3, it's going to get really messy and you probably won't even be able to answer the question. So we know that our matrix that we're dealing with is 2 by 2. And this is important because this question is basically the bonus question in assignment 2. So if it's 2 by 2, it's going to have entries M11, M12, M21, and M22. So we get this from basically that underlined green portion right there. So this is the first part. The second part that we have to kind of realize is talking about eigenvalues. How do we determine eigenvalues? Did we have a formula for eigenvalues? Yes. What was the formula? Exactly. So we know that the determinant, when we're solving for eigenvalues, we're looking at this equation. The determinant of m minus lambda I is equal to 0. This comes right from the slides. From there, I can write it out, actually. So what we're going to do is we're taking a determinant, so I'm going to put in these kind of absolute bracket signs, and I'm going to have m11 minus lambda. I'm going to have m12, I'm going to have m21, and I'm going to have m22, again, minus lambda. Now the key here is that this determinant must equal 0. So if a 2 by 2 matrix, we know that it must equal 0 when we take the determinant. So let's take the determinants. Again, the best way I like to do it, I like to draw my little fish. So I go from here to here, and then I subtract m12 minus m12. So I'm just going to erase that because that looks kind of bad. So what happens is we basically get this. We get m11 minus lambda multiplied by m22 minus lambda, and then minus m12 multiplied by m21 is equal to 0. Can everyone see where I got this equation from? Yeah? So what do we do next? If I said we have a 2 by 2 system, what kind of equation is this actually? Quadratic. You guys remember quadratic formula? Yes. So whenever you have something quadratic and trying to solve, best way to do it is to put it into a quadratic form. So all I'm going to do is I'm going to take this equation that I have above and I'm going to simplify it into the following. Lambda squared minus, and then I'm going to have a coefficient, which is going to be m11 plus m22 multiplied by lambda. And then I'm going to have plus another coefficient, which is m11 m22 minus m12 m21. And all of this, of course, is equal to 0. And we know with our quadratic formula, we can solve for lambda. You guys remember the quadratic formula? No, I don't either. I always have to Google it. So what happens is lambda, using quadratic formula, is negative b. So that'd be, actually, we'll highlight them. So this coefficient right here is b. The coefficient here is a. And then this last coefficient over here, that is c. So it's equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. So that's quadratic formula. Nothing too crazy. Well, actually, your grade 11 teacher would probably be freaking out. Not here. So now we have kind of a solution for lambda, these eigenvalues. And if we look up here, the question says, find a matrix that does not have real eigenvalues, meaning complex eigenvalues. How do we get a complex number? Negative square root. So if I were to come down here and look at this right here, what would have to be negative for us to get a negative eigenvalue, or a complex eigenvalue? Exactly. So what would happen is the only way to get a complex eigenvalue is to have a negative number inside of the square root. So this right here has to be negative. Make sense to you guys? So if I were to come down here and I were to say, all right, well, we know that b squared minus 4ac has to be less than 0. If I were to satisfy this, I'm going to get complex eigenvalues. So what I can do is I can write it out. I can say, all right, well, b, if we look up top, is negative m11 minus m22. So I can come down here and say, all right, well, we got negative m11 minus m22 squared minus 4, that stays the same, multiplied by a. What is a? 1, nice and simple. And then multiplied by c. If we look at c, it's m11 m22 minus m12 m21. So m11 m22 minus m12 m21. And again, for this to be negative, this has to be less than 0. So then it just becomes a game of simplification. What actually happens when you write it out is you guys will get something like this. You'll have m11 squared plus m22 squared minus 2 m11 m22, and then you'll get plus 4 m12 m21, and again less than 0. So the reason why I made this a bonus question is because it is a lot of deriving, but there is some special features. And that's this. Let's see if we have any math nerds in the lecture today. If I were to look at this component as a whole, will that ever be negative? It's one of those funny math proofs. That right there, that'll never be negative. It is impossible, no matter what you choose for 1, 1, and 2, 2, that'll never be negative. So that's going to be the secret to this week's assignment, because again, it's very similar to this question. This right here will always be a positive value. So if I want this less than 0, and this first part's always going to be positive, the only way I can make it 0 is by making this part over here extremely negative. Can I make that part negative? Yeah. I can have m12 as a positive. I can have 21 as a negative. Positive, negative, they form a negative. And all I need to do is make sure that that term at the end outweighs this initial term. If you guys can choose m12 and 21 such that it outweighs that first term, you guys will end up getting a negative. Does that make sense to you guys? Now, let's go to the last part of the question, and it says this. Can a symmetric, I guess I used red on red writing, it doesn't really show up. Now let's go to green. Can a symmetric matrix have non-real eigenvalues, or complex eigenvalues? Now, if we're looking at this matrix here, this 2 by 2 matrix, what would it mean if it is symmetric? We're going to talk about this later on, so don't worry if you don't know. Anyone want to take a guess? Exactly. M12 is actually equal to M21. So M12 is equal to M21. That's if it's symmetric. Basically saying that every off-diagonal component are going to be equal to each other. Now, if that's the case, and M12 is equal to M21, can this ever create that very large negative that we need? No. Because even if they're both negative, it forms a positive. If they're both positive, well, it's going to be positive. So to answer the second question here, can a symmetric matrix have non-real eigenvalues? Well, the answer is going to be no. Now, this is actually going to be important to us because all of the matrices we will deal with are going to be symmetric. Our stress tensor, or stress matrix, is symmetric. Our strain tensor, or strain, is going to be symmetric. Now, what do you guys think? Is that realistic? Do you think that that's just a simplification of this course? Or do you think it's actually realistic that the matrices governing stress and strain in real objects are symmetric? Who thinks it's just a nice simplification to make our lives easier? Who thinks it's realistic? It's actually realistic. Because if we were to look at an object, and let's say that I have a wall here, and I have an object, and now we're to put some force on this object. It's going to start squishing together, right? But if I were to move it to the other side, or move the wall to the other side, and now I have my box over here, and I'm applying load like this, and the force is the same on both, we expect that the response to the box is going to be the same. The left side or the right side, either way, our box is getting squished. And the response is going to be the same. If I were to push this table this way, using the same force, and then go to this side, same force, the response is the exact same. That's why things in real life are symmetrical. The loading direction doesn't really play a role. There is very specific scenarios in plasticity. So let's say that I were to push my concrete beam and crack the shit out of the bottom of it. Well, when I start applying load the other way, since this is damaged, it will behave differently. But in this course, we don't talk about anything damaged. Nothing gets damaged, so the response in any direction will be identical as the opposite direction. Hopefully that makes sense to you guys. So that's it for today's lecture. For those in the seminar, I will see you guys there. And if you guys have any questions, please feel free to come and ask me.